At first light, Devil's Tower does not look like a mountain. It looks cut. A grey cylinder rises out of the Wyoming plain with fluted sides, a flattened crown, and vertical grooves so regular they seem measured by a machine. From the road, it has the proportions of a stump left behind after something immense was removed. The surrounding hills only make the contradiction sharper. They slope and crumble like ordinary landforms. This thing does not. It stands apart, too steep, too symmetrical, too abrupt, as if the landscape around it belongs to one story and the tower belongs to another. There is the shape itself, and then there is the uneasy fact that almost everyone who sees it reaches for the same forbidden comparison. The accepted explanation arrives quickly. Devil's Tower is said to be igneous rock, phonolite porphyry, pushed upward as magma, cooled slowly underground, and later exposed when the softer material around it eroded away. Its columns are explained by cooling fractures, the same process that produces hexagonal joints in basalt cliffs and lava flows. Flat-top mesas are explained differently, but within the same geologic grammar. Horizontal rock layers, a hard cap, softer strata beneath, then time, water, frost, and gravity cutting away the edges until only isolated tables and buttes remain. On paper, the sequence is orderly. Uplift, intrusion, deposition, erosion, exposure. Each term has a place, each feature can be filed, and yet what remains on the ground often feels less complete than the explanation meant to settle it. The problem is not that geology has no answers. How much the problem is that the answers can become so broad they explain almost any shape after the fact. A mesa is flat because hard rock resisted erosion. A tower is vertical because jointed rock fractured that way. A butte is isolated because everything around it wore away. Those statements are true as far as they go. But the eye keeps returning to form. Why do so many of these isolated masses resemble severed biological structures more than collapsed hills? Why do some stand with cylindrical walls, radial textures, and level tops that read immediately and physically like stumps? And why does the comparison persist even among people who have never heard the theory? The hidden theory, stated carefully, is not that every flat-top mountain on Earth was once a tree. It is narrower, stranger, and harder to dismiss cleanly. However, it is that a small class of isolated towers, mesas, and flat-top formations may be the mineralized remains of biological structures from a world whose scale is no longer recognized, then buried, altered, and recategorized as ordinary geology. In this view, some mountains are not mountains in origin, but remnants. Some columns are not only fracture patterns, but overprinted anatomy. Some landscapes are being read as rock alone when they may record a lost interface between biology, sediment, heat, and catastrophic burial. That is not a proof. It is an investigative possibility. The question is whether the record has been tested against it seriously enough to rule it out. Start with scale and silhouette, because that is where the suspicion begins. A normal mountain grows from a system of slopes, ridges, at a structural continuity with the land around it. A stump does not, it interrupts. Devil's Tower rises almost vertically for hundreds of feet before rounding slightly at the summit. Many beauties of the American Southwest do something similar on a broader footprint. Steep sides, sudden shoulders, and a top surface that looks truncated rather than peaked. The same profile appears in South American tepuis, in isolated table mountains in Africa, in basalt-capped mesas, in towers left standing after surrounding strata have vanished. Officially, these are different classes of landform formed by different processes in different rock types. But the shape language repeats: flat crown, sheer wall, isolated survival. The pattern does not disappear just because the labels change. Then there is texture. On formations like Devil's Tower, and the vertical grooves are usually described as joints, shrinkage cracks frozen in stone, as hot rock cooled and contracted. That explanation is well established, but it also leaves a visual fact sitting in plain view. The grooves run downward like grain. In cut wood, the surface often exposes bundled vertical fibers separated by natural lines of weakness. In columnar rock, contraction produces polygons, usually hexagons, packed side by side. The mainstream model explains the geometry. What it does not explain away is why the result so often resembles a cut organic cross-section to the naked eye. That may sound superficial until one remembers how much of field science begins with morphology. Scientists trust form when classifying shells, bones, leaves, fractures, and faults. Form is not everything, but form is not nothing. Under measurements deepen the unease. A flat top matters because it implies a boundary event. In ordinary mountain building, peaks are usually irregular because stress, faulting, and weathering do not cut landscapes like a blade. In mesas and buttes, the top surface is preserved because a hard layer resists erosion. That is the official explanation. But on the ground, many of these tops are not merely broad plateaus. They are startlingly level termination surfaces over bodies that narrow or steepen below, as though a larger vertical form once continued upward and no longer does. In some cases, the cap is a distinct lithologic layer. In others, the summit belongs to the same mass as the sides. What matters is not one example, but the repeated impression of truncation. There is a difference between a hill worn down and a thing that looks ended. The eye registers that difference before language catches up. Old photographs sharpen it further because they preserve the moment before interpretation hardens. 19th century survey images of towers, monoliths, and buttes often show them without explanatory text, just bare stone rising from plains, forests, or river valleys. In that state, before the viewer is told what category to use, the forms read as artifacts, amputations, remains. Early observers reached for words like tower, stump, post, organ, chimney, monument. Those terms were not scientific conclusions, but they mattered. They were shape descriptions from people seeing the structures without a century of sedimentological framing. What changed was the explanation. The visual shock stayed the same. The record is still there. We inherit the labels after the fact and forget that many of these places first entered public memory as objects too singular to fit comfortably inside ordinary terrain. The next block of evidence is not about mountains at all. It is about wood turning to stone. Petrified forests exist. Silicified trunks exist. Growth rings, bark textures, cell structure, and root systems have all survived mineral replacement in the fossil record. That alone does not validate giant stumps in the landscape, but it removes a common reflex dismissal. Organic material can become rock. It can retain structure while changing composition. It can survive burial, heat, fluid movement, and immense spans of time. Once that is admitted, the real dispute is no longer whether stone can preserve biology. It is whether biology of a radically larger scale ever existed, and whether some formations currently treated as purely geologic have been tested against that possibility rather than excluded by assumption. The issue is not mineralization. The issue is scale, classification, and the limits of accepted precedent. Supporters of the giant tree interpretation often point to branching systems in the landscape, ridges radiating from central monoliths, hardened linear features extending across softer ground, spoke-like patterns seen from above. Mainstream geology has names for these too: dikes, sills, feeder systems, resistant fins, differential erosion. In places like Shiprock, the radiating walls are understood as igneous intrusions exposed after surrounding rock vanished. That explanation fits the chemistry and structure, but the alternative reading notices something else. When a central mass stands isolated and hardened lines run outward from it into the buried substrate, the resemblance is not to a random hill. It is to anchoring architecture. Root, brace, conduit, support. Perhaps the resemblance is accidental, perhaps not. What matters is that the pattern recurs often enough to deserve comparison across disciplines rather than inside geology alone. Here the mainstream explanation deserves to be stated fairly because parts of it are strong. Columnar jointing is real. Caprock erosion is real. Volcanic necks and plugs are real. Intrusive bodies do cool into polygonal columns. Horizontal sedimentary layers do protect flat tops until erosion isolates them. A great deal of the visible material in these formations behaves exactly as geologists say it should. While the mineral composition of Devil's Tower is not wood, the surrounding strata in many mesas clearly document deposition, uplift, and long erosion. None of that should be ignored, but fair acknowledgement also means identifying the point where the explanation stops being specific and becomes total. It explains rock type, it explains fracture mechanics, it explains survival through erosion. What it does not fully explain is why such different processes keep delivering the same severed grammar of form, nor why alternative tests are treated as unserious before being performed. Maps widen the issue from single landmarks to distributed pattern. Look at the American West from above, and isolated buttes stand like cut posts in fields of sediment. To look at Tepui country in Venezuela, and ancient table mountains rise from rainforest with walls so sheer they seem detached from all ordinary weathering logic. Look across deserts, badlands, plateaus, and uplifted basins on multiple continents, and the same motif repeats. Detached crowns, abrupt escarpments, solitary remnants, repeated flatness at elevation. Officially, these are products of local lithology and regional history, and that is partly true, but recurrence changes the psychological burden. One impossible object can be dismissed as coincidence. 1,000 variations of the same impossible object become a category. The theory gains force not because one mountain looks like a stump, but because the landscape keeps manufacturing stump-like forms across settings so different that the shared silhouette begins to matter more than the separate labels. There is also the question of burial. If these formations were once larger vertical bodies, why are only the upper sections visible? The alternative model answers with sediment, ash, flood deposits, marine incursions, and deep time mineral replacement. In other words, the trunk below the visible rise is not missing. It is entombed. Conventional geology already accepts burial on a vast scale. Entire forests have been covered. River systems have been inverted. Lava has sealed valleys. Ancient soils have vanished beneath younger layers. What the hidden theory suggests is not a new mechanism, but a new target. And the lower portions of these structures may not have weathered away at all. They may remain locked inside the matrix now called country rock. What looks like a mountain growing out of the ground may instead be a remnant emerging from it. The difference is profound. One model begins with bedrock, the other begins with a buried body. Engineering details complicate the picture in a different way. When quarrymen cut stone, fracture planes matter. When foresters cut timber, grain matters. In photographs of certain towers and basaltic cliffs, the regularity of the sidewalls creates a strange overlap between those two worlds. Some faces look as if they have failed along prepared seams. Others appear peeled, exposing long internal strands. Geologists read these as cooling joints, exfoliation, spalling, tarless production. That is the orthodox reading, and often it is sufficient. But there are cases where the combination of vertical segmentation, circular or oval plan form, and abrupt upper termination creates an object that behaves visually less like a cliff face than like a cross-cut section. This is where public unease lives. People may not know igneous petrology. They know what a cut surface looks like. They know when a form seems processed rather than simply weathered. Historical timing adds another layer. Many iconic formations entered formal study during the period when geology was consolidating itself as a discipline and needed stable categories quickly. The impulse then was to sort by rock type, strata, eruption, intrusion, faulting, and erosion. That was a scientific achievement. But it also created an administrative habit. Once a structure was placed into a recognized box, inquiry narrowed to mechanisms inside that box. A tower classified as an intrusion would be studied as an intrusion. A mesa defined by caprock would be discussed as caprock. Cross-domain hypotheses, especially those involving biology at landscape scale, would not merely seem wrong. They would appear illegible. That is how ideas vanish without anyone having to suppress them. Not through a dramatic conspiracy, but through taxonomy, through paperwork, through the ordinary force of institutions defending their boundaries. The language of land management shows the same thing. Parks, monuments, surveys, mining offices, and academic departments all divide the world into resources, hazards, formations, and protected features. But those legal definitions are practical. They also become intellectual walls. Once a structure is managed as rock, no one budgets to test whether it preserves macrobiological architecture. Once a surface is classified as a natural monument, the question of origin tends to freeze around public consensus. Samples may be taken for age and composition, but not for the broader comparison the hidden theory would require. Anatomy-like patterning, mineral pathways associated with replacement, surrounding burial geometry, or systematic analysis of stump form sites across continents. The absence of such work is then used as proof that the theory lacks evidence, but absence of testing is not the same as disproof. Bureaucracy can look a lot like certainty from a distance. Another anomaly lies in the missing infrastructure of the official stories. If a volcanic neck remains, where is the rest of the volcanic architecture in comparable scale and clarity? Often the answer is erosion, and sometimes that answer is reasonable. If a mesa survives because resistant caprock protected it, what exactly created the repeated abruptness of the cap boundary over so many isolated blocks? The explanation is again differential weathering, and again that may be correct, but the cumulative effect is revealing. The orthodox account frequently depends on removed context. The volcano was there, then eroded. The plateau was there, then eroded. The surrounding support was there, then eroded. Removal does enormous labour in these narratives. Perhaps that labour is justified. Yet when the missing portions consistently correspond to the very features that would make the object look less like a stump, that skepticism becomes rational. There is a deeper pattern hidden inside plain geology itself. The science openly describes relief inversion, silicification, mineral replacement, lithification, burial, uplift, unconformities, and erosional windows. These are powerful ideas. They mean Earth can preserve one thing while making it look like another. River channels become ridges, forests become stone, seafloors become mountains, entire environments are transformed, then exposed in fragments. That should make us more careful, not less, when faced with landforms that appear biologically suggestive. The hidden theory does not need a magical Earth, it only needs the Earth geology already describes, operating on material we have misidentified from the start. If landscapes can invert, if wood can petrify, as if forms can survive while composition changes completely, then categorical humility becomes the logical position. The stone remembers even when the explanation forgets what question it was meant to answer. At this point, the obvious objection returns. If giant trees once existed on such scale, where are the branches, the leaves, the forests, the soils, the ecological record? It is a serious objection. The alternative model answers in fragments. Some branch systems may be read as ridgelines or dikes. Some forest scale remains may be buried beyond recognition under basin fill, lava provinces, or marine sediments. Some evidence may have been destroyed by the same catastrophic processes that preserved only the most durable cores. None of these replies is complete, but incompleteness cuts both ways. As the orthodox picture of many isolated towers and mesas also depends on absent worlds reconstructed from remnants. We accept those reconstructions because the category is familiar. The real question is whether unfamiliar reconstructions are being rejected because the evidence fails, or because the premise would force too much of the map to be read again. What matters most is not proving that every stump-like mountain is a stump. That is neither necessary nor persuasive. What matters is the repeated mismatch between the visual language of these forms and the confidence with which the official account closes the case. A theory becomes dangerous to institutions not when it is wild, but when it is testable and embarrassing. This one is testable in principle. Comparative morphology across sites. It's a deep subsurface imaging around candidate formations. Mineral pathway analysis looking for replacement signatures inconsistent with ordinary intrusion alone. Structural mapping of radial features without assuming volcanic origin from the outset. Cross-disciplinary teams instead of siloed departments. If those studies were done rigorously and failed, the theory would weaken. But if they have not been done, then dismissal is not science. It is posture. Seen this way, the subject stops being a question about mountains and becomes a question about categories. What if some objects in the landscape survived because they were too large, too altered, and too inconvenient to be recognized for what they began as? What if the reason they seem impossible is not that they are impossible, but that we have inherited a vocabulary built to make them ordinary? The flat top becomes a severance plane. The columns become surviving internal structure. The surrounding sediments become burial rather than birthplace. The isolated monument becomes not a leftover hill, but the exposed top of a body still embedded in strata below. It sounds strange only until one notices how often the land itself seems to insist on that reading, against the patience of every official label placed over it. And so the argument compresses into a final reframing. There are towers that look cut, mesas that look terminated, landscapes full of solitary crowns, rising from material that seems less like parent rock than like burial. There are real geological processes that can imitate those forms, and they must be taken seriously. But there's also a repeated morphology that has never quite stopped provoking the same thought in those who stand beneath it. Not because they are irrational, because the object itself pushes the mind there, the record is still there. What changed was the explanation. The pattern does not disappear, it only gets renamed. If these flat-top mountains are exactly what the textbooks say, then stronger testing would only strengthen the textbooks. But if even a fraction of them are remnants of something older, larger, and biologically stranger than the present model allows, then the stakes are much higher than a disagreement over scenery. They reach into chronology, extinction, classification, and the limits of what modern institutions are prepared to notice once a story has already been filed. The real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.